Okay, so today I'm going to go over a problem involving a sequence. This is from IMC 2019. This is number 4. So it is giving us, the problem is giving us a sequence of numbers and given a recursion, and it is asking us to show that this, in fact, all of the terms of this sequence are integers. Okay, so if we think about this one, if you are dealing with a recursion, the best method or the most natural method would be to use induction. So we could assume that an is an integer and then try to prove that an plus 1 is an integer, or assume that all of the numbers from a1 all the way to an are all integers and then prove that the next one is an integer. But there's a huge obstacle for doing that in this problem. If you divide both sides by n plus 3, you realize that there's a fraction. So you would get 6n plus 9 an plus 1 minus nan divided by n plus 3. You could show that these numbers are all rationals, but showing that they are integers is not really possible using this method. You would have to somehow show that the numerator is divisible by n plus 3. But you might think that, okay, maybe I can use induction to prove that the numerator is divisible by n minus 3. And that's a good thought, but because again, this sequence is given by a recursion. So it's a good idea to use induction. However, the problem is if I want to use the fact that n plus 3 divides 6n plus 9 times an plus 1 minus nan, then the next step would be to show n plus 4 divides something similar. 6n plus 15, an plus 2 minus n plus 1, an plus 1. That is very problematic for me because how am I going to go from mod n plus 3 to mod n plus 4? Those are completely separate issues. So that doesn't seem plausible either. So what else can we do? One of the techniques that we can usually use to show a sequence is of all integers is to, again, as I said, use induction. But if we can somehow turn this recursion into a recursion that doesn't involve n plus 3 in front, so if we can write an plus 2 equals something in terms of like an f of a1 all the way to an in a way that the right-hand side has all integer coefficients, basically integer terms, then we are done. So if I can write down a recursion in a way that the right-hand side, or this could be an plus 1, the right-hand side doesn't look like what I have here, which is there's a denominator of n plus 3. So if I did not have this n plus 3 here, then I could easily show that an plus 2 is in fact an integer by using induction. So this seems maybe more plausible. It's not clear how that can be done, but it seems certainly more plausible. Maybe I can show that an is in fact going to satisfy a different recursion. So can we find a different recursion for an? If I can find a different recursion for an, then I should be able to solve the problem. Okay. So the question is now, how am I going to be able to find a different recursion here? You could start manipulating that and see what you can get, but there's not much you can get by just manipulation of this recursion. What I do see is I have the coefficient of x plus n plus 3 in front of a n plus 2, and I have coefficients here and here as well. So when I have coefficients of n plus 1, n plus 2, n plus 3, things like that in front of an plus 1, an plus 2, that makes me think of using power series and differentiation. So if I differentiate x to the power of n, I'm going to get n x to the power of n minus 1, which is kind of similar to what I have here. I have these coefficients of n plus 3, 6n plus 9, and n in there. So a technique that is useful in finding sequences is what we call generating functions. So let's say f of x is the sum a n x to the power of n, and of course n starts from 0 to infinity. I do know that a0 is 1, and I know that a1 is 2. So I want to see what I can get from here. So for example, if you differentiate that, this gives you the sum n a n x to the power of n minus 1. Of course, the very first term is just a constant. A0 is a constant. So you can just start from 1 to infinity. So it seems reasonable to work with this function, given that my recursion has some linear coefficients. So differentiating it once hopefully would help us with finding this power series. If I can find this power series, then I would be able to solve for an, find an, or at least use that to find a different recursion. We'll see. Maybe that doesn't work, but we won't know until we try. So I'm going to repeat the recursion. I'm going to rewrite the recursion, and I'm going to multiply both sides by appropriate powers of x, and then I'll add them up, and then that gives me the generating function, that power series. So 6n plus 9 a sub n plus 1 minus n a n, and n is greater than or equal to 0. So we will multiply by powers of x. So perhaps let's multiply both sides by x to the power of n plus 2. But I can only start summing from 0 to infinity. It can't go below 0. So that's equal to the sum 6n plus 9 an plus 1 x to the power of n plus 2 minus n a n x to the power of n plus 2, n equals 0 to infinity. Okay, so far it seems you may be in the right track, but we'll have to see. If I had n plus 1 rather than n plus 2, I'm sorry, if I had n plus 2 rather than n plus 3, then I could write down as a derivative. So let's factor an x from here and write it down as n plus 2, an plus 2, x to the power of n plus 1, n equals 0 to infinity. But then there's another term here. There's the last term, which is just, I have one of these, an plus 2, x to the power of n plus 2, n equals 0 to infinity. So that equals, on the right, I can get something similar. I'm going to turn that into something that looks like its derivative. So I'll have to factor x squared. So I'll get x squared, the sum, n equals 0 to infinity. So if I want x squared, if I factor x squared, then I need n x to the power of n, which I'm going to get, and I need n plus 1 an plus 1. So I have a 6 in front, so I'll just put a 6 in front, n plus 1, an plus 1, x to the power of n. So that's going to give you the 6n plus 6 plus 3. I'm going to factor 1x. That's an plus 1, x to the power of n plus 1, n equals 0 to infinity. Minus Okay, so I can do the same thing for the last one, except I already have the n, which is good. So I'm going to factor x cubed. The sum n equals 0 to infinity. In fact, you could just start from 1 to infinity because the very zero term is just 0. a n x to the power of n minus 1. So that's nice. This is something that we can use to relate the recursion with the power series that we started with, or what we call the ordinary generating function. So that's, so far it's good. So this one, as I said, this is essentially the derivative. So that's the derivative of f, except it's missing, in fact, one term. So it starts from a2, it starts from 2a2x, but it needs to start from a1. So it's f prime of x minus a1 plus. The next term is essentially f of x, although it is missing the very first term, a0, and it's also missing a1x. So it's missing these two. On the right, we have I'm going to factor the 6 here, 6x squared. That is essentially derivative, except that we have to make sure that nothing is missing, and in fact, nothing is missing. So it's a1, the very first term is a1 x to the power of 0, which is exactly what we need in derivative of f, plus 3x. Okay, this part is just exactly f of x minus x cubed, and this part is again exactly f prime of x. So that's so far good. So we'll plug in the values and we'll move everything to the same side and see what it gives us. So taking these three that have f prime, moving them to the left, we get x cubed minus 6x squared plus x, f prime of x. Then I'll see what I have for f of x. So I have a 1 here and a 3x here, so that becomes 1 minus 3x, f of x. And then I have the terms with without any f of x. So these are the three terms without any f of x. A1 was 2, A0 was 1, and this is 2. So we'll get negative 2x from the first term, negative 2x here, 4x, and that's 1. So that's equal to 4x plus 1. Okay, so let me just make sure. Yes, I have this one. This term should be f of x minus a0. So I should have minus a0 here. That gives you another 1 here. And then the last one is minus x cubed f prime of x. So I in fact get x plus 1 only for here because yeah, those 4x and 3x cancel, negative 4x on the left and negative 3x on the right cancel, and you get this one. Okay, so we ended up with a differential equation now. So now we can see if we would start seeing if we can actually solve this differential equation. And if we can solve this differential equation, that means we can find f of x. And if I can find f of x, then I would be able to find an, which is the objective here. So this is a first order linear differential equation. I'll just divide off and I'll try to find an integrating factor. So I'll divide off by x cubed plus minus 6x squared plus x, and then I'll find the integrating factor. So if you multiply by integrating factor of mu, you want the derivative of this to be equal to mu times x plus 1 over, if you factor the denominator, it might be a good idea. We'll see. You want this, you want to have that. But that means if you expand this one, you get mu times f prime, and then you get mu prime times f. So what that means is that mu prime must be mu times 1 minus 3x over x times x squared minus 6x plus 1. So this gives you mu prime over mu equals 1 minus 3x over x times x squared minus 6x plus 1. So I need to be able to integrate the right-hand side. So that's what I need to do. The right-hand side, you can do it, you can integrate using partial fractions. So that's a over x plus bx plus c over x squared minus 6x plus 1. So this gives you 1 minus 3x equals a x squared minus 6ax plus a plus bx squared plus cx. So a plus b is equal to 0. That's the coefficient of x squared. Coefficient of x gives you c minus 6a, that is negative 3. And the constant term is a, which is 1. So that gives you a is 1, b is negative 1, and c is 3, which gives you 1 minus 3x over x times x squared minus 6x plus 1 is equal to 1 over x 1 over x plus minus x plus 3 over x squared minus 6x plus 1. Okay, so I'll have to integrate that. 1 over x is easy to integrate, and fortunately the derivative of the bottom here becomes the top. So if you integrate that, you get natural log of x plus derivative of the bottom becomes 2 times the top. So if you differentiate that, you get 2x minus 6, which is 2 times x minus 3. So I guess it's like negative 2 times the top. So natural log of x plus, if you want to do u substitution, that might be a good idea. So I'll do u here for the denominator. And the numerator is going to be minus 1/2 du. So that would be natural log of x minus 1/2 natural log of u plus a constant. So that is natural log of x over root u plus a constant. Perfect. So that's nice because we are able to find mu here. So mu would be x over x squared minus 6x plus 1 to the power of 1/2. So that is, because remember that the derivative of the left-hand side is, I'm sorry, the integral of the left-hand side is natural log of mu. So mu would be that, which means I can actually solve this differential equation. So that gives me x over x squared minus 6x plus 1 to the power of 1/2 times f of x prime is equal to the other side multiplied by the same thing. So when you multiply the other side by the same thing, you get x plus 1 on top, and then you get x squared minus 6x plus 1 to the power of 3/2 at the bottom. So if I just scroll up to show you where we have that. Yeah, this is what I have. So if I multiply that by x over x over x squared minus 6x plus 1 to the power of 1/2, I get this. Okay. So now I have to integrate that.